Welcome to Unit 14, Video 3, Collision Theory. By the end of this video, you should be able to explain how and why reactions happen in terms of collision theory. You should be able to label and interpret an energy diagram of a reaction. And you should be able to explain why certain factors speed up the rate of a reaction in terms of collision theory. Collision theory is a theory used to explain why a reaction will occur. According to collision theory, molecules must collide in order to react. These collisions must result in the breaking of reactant bonds. Therefore, only a small fraction of all molecular collisions will be effective or will produce a reaction, because not every collision will result in the breaking of a bond. There are two factors that determine whether or not a collision will be effective or whether or not the collision will break bonds and produce a reaction. The first is the energy of the collision. So the molecules must collide with enough energy to actually break the bonds. Imagine we have two people and we define an effective collision as one in which one of the people gets knocked over when they collide. If those two people run full steam ahead into each other, they'll definitely knock each other over. However, if they walk very slowly into each other, they probably won't. We also have to have the proper molecular orientation, meaning the molecules must be pointing in the correct directions. Looking at the first two pictures here, you see that our reactants are not oriented properly in order for a reaction to occur. The oxygen has to collide with the nitrogen end of the molecule in order for a reaction to occur, and in these first two cases, they haven't. However, in this example, our oxygen is oriented correctly with our nitrogen in order to produce an effective collision. We can represent a reaction process using a diagram, but before we do so, there's some vocabulary we need to know. First is the activation energy, which is abbreviated capital E, small a. This is the energy that must be overcome to produce a chemical reaction. In other words, it's the minimal energy required for the reaction to begin. You can think about it as the energy required to produce a fruitful collision. Some examples of activation energy that you might be familiar with are the striking of a match. If you hold a match in oxygen, it won't light until you strike it because it needs some energy to get going. That's the energy of activation. Likewise, when we light the magnesium in the Bunsen burner, here we're overcoming the activation energy to get magnesium and oxygen to react. Recall that we don't have to keep the magnesium in the Bunsen burner once it's lit. Likewise, you don't have to continually strike the match once it's lit. The activation energy is simply the energy added to get the reaction going. Once it's going, it will proceed without additional input of energy. The activated complex is a transition state. This is a temporary arrangement of atoms that occurs at the peak of the potential energy barrier. The activation energy is essentially the energy required to achieve this transition state. Let's look at this on a diagram. Here's an energy diagram for an exothermic reaction. First, notice that the reactants are higher in energy than the products. This means that our delta H will be negative. This reaction is releasing energy. If you think of delta H as the difference between the final and the initial, you'll see that our final is lower than our initial, giving us a negative delta H. The other thing you should notice here is that our activation energy is represented. Activation energy is the difference between the energy of the reactants and the top of the potential energy barrier. This is the amount of energy required to get the reaction started. It's important to note that activation energy is not included in the delta H. Delta H is just the difference between reactants and products. You'll also notice the activated complex is represented here. We can kind of think of the energy diagram as a roller coaster. Imagine that you're on the roller coaster. You need to put some energy in to get the roller coaster to the very top of the hill. This is your activation energy. At the top of the hill, you know when you get that feeling that you know you're about to drop and your stomach kind of gets a little funny because you know that the big drop is coming? That's sort of your temporary arrangement before the reaction proceeds full steam ahead. That's akin to the activated complex. The activated complex is a temporary arrangement of atoms at the top of that potential energy barrier. Looking now at an energy diagram for an endothermic reaction, we see that in this case, the energy of the reactants is lower than the energy of the products. Therefore, a delta H will be positive because energy is going into the system. In this case, our activation energy, which again is the difference between the reactants and the top of the potential energy barrier, is here. Notice it's much larger for this reaction. Here's a potential energy diagram for us to label. We'll label it together. First, let's find the energy of the reactants. The energy of the reactants is represented by A. That's the energy that we start at. Therefore, the energy of the products is going to be down here, D. Now let's find the activation energy. Activation energy in this case is represented by B because it's the difference between the energy of the reactants and the top of the potential energy barrier. Line C represents the energy of the activated complex because the activated complex is the temporary arrangement at the very top of this bump. One thing that's not labeled with a letter here is the delta H. The delta H is the difference between the energy of the reactants and the energy of the products. Therefore, we can draw in an arrow to represent delta H. Notice that this is an exothermic reaction. We know this because our reactants are higher in energy than our products. Looking at this potential energy diagram, notice that here our y-axis is actually labeled with kilojoules of potential energy. From this diagram, we're actually able to determine values. Let's do one together, then you can try the rest on your own. First, let's find energy of reactants. The reactants are here, so our energy of reactants goes from here to here. This means that we have 40 kilojoules for our reactants. Pause the video here and try to determine the rest of these values. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. We talked briefly before about some factors that affect the rate of a reaction. A reaction rate is how much reactant is converted to product per unit time, usually per second. There are 5 factors that affect the reaction rate: temperature, concentration, surface area, catalysts, and nature of the reactants. Let's look at each individually. Let's look first at temperature. If you increase the temperature of a system, this means that the particles will be moving around more quickly and therefore will collide with more energy. Higher temperatures mean higher molecular speeds, which means more frequent high-energy collisions. This will mean more collisions that are capable of breaking bonds and a faster reaction. Looking at this bell curve here, we see that at the lower temperature, T1, very few of the collisions have enough energy to overcome the activation energy barrier, so very few collisions will be effective. However, at higher temperatures, T2, more of our collisions will have sufficient energy to be effective. Thinking about concentration, a higher concentration will mean more particles in a given volume. This will result in more frequent collisions. On the left, you see that there are very few molecules. Therefore, you won't get all that many collisions. Imagine 5 or 6 people went to the gym and ran around. They wouldn't run into each other all that often. A higher concentration, however, means more particles, which means more collisions. Now take those people in the gym and add 50 more people. If we had upwards of 50 people running around the gym, they'd run into each other pretty often. This is also true for surface area. When there's more surface area, this means that more particles are exposed. This will also result in more frequent collisions. In both cases, we have more frequent collisions, therefore we'll have more effective collisions. If you play the lottery once, you have a small chance of winning. But if you play the lottery 50 times, you have a much greater chance of winning. Likewise, the more collisions you have, the more chance that you'll have an effective collision. We can also add a catalyst. A catalyst is a substance that speeds up a reaction without being consumed. Notice that it's a substance, so energy does not count as a catalyst. A catalyst works by lowering the activation energy. It allows for a new mechanism for the reaction to proceed that has a lower activation energy than the original. Since the activation energy is lower, more molecules will have the activation energy required at a given temperature. It's important to note that the addition of a catalyst will not change the delta H. Here's a diagram. Here's an energy diagram representing an uncatalyzed and a catalyzed reaction. The red line represents the energy diagram for the regular reaction without a catalyst. Here, its activation energy is the difference between the reactants and the top of the bump, so we have this red arrow. The green dotted line, however, represents the reaction which has had a catalyst added to it. Here, the reactants still have the same energy, but the top of the bump is lower. Therefore, we have a lower activation energy. Your roller coaster doesn't have to climb as high before it starts to drop. Notice that in both cases, our delta H has not changed. Delta H is the difference between the reactants and the products. Therefore, since the reactants and products have not changed, delta H does not change. Finally, nature of reactants. Reactions that involve a small rearrangement of bonds just take less time. For instance, if we have 2 molecules of hydrogen and 1 molecule of oxygen, we only have to break 3 bonds and form 4. However, take this example of a very complex organic reaction. Look at all the bonds that need to be broken and reformed. The reaction on the right will take far longer than the reaction on the left. This brings us to the end of this video. Let's review our goals. First, we looked at how and why reactions happen in terms of collision theory. Recall that a collision must occur for a reaction to happen, and that collision must be effective. So it has to have the right energy and the right orientation. Then we labeled and interpreted an energy diagram. And finally, we talked about why factors such as temperature, concentration, surface area, and nature of reactants speeds up the rate of a reaction.